Welcome back, friends, to a new lesson in the YBite Algorithms and Olympiad track. We call this Time to Search. Now, this lesson is all about search algorithms. It turns out search is a fundamental problem in computing, and that's what we are going to look at. In fact, before getting started, search is something that we do as part of our day-to-day lives a lot. I mean, for example, when we go to a new place, we look for things. Even sometimes at home we lose things, or we may want to look for something in a book, we may want to look for something in a map, and so on. So search is something that really is integral to our life, and so it is in computing. In this set of videos, we look at the search problems as it applies to computing. But before going there, let's just recall what we have learned so far. We learned in the last lesson that look, naive algorithms get us started, but they can be quite inefficient. And this inefficiency is seen the most when we make the size of the problem large. So, for example, when we give a large prime number to be tested, the inefficiency becomes very, very glaring and we can immediately feel it. Just like earlier, we saw that smart ideas can be used to improve efficiency, make the algorithm more efficient. Remember, the basic question to ask is my algorithm doing more work than what is needed? It turns out that sometimes structure in the data also helps us, and this is true for a searching problem, right? So first, let's define what a searching problem is, and then we'll see how things follow from there, right? Basically, the problem is that, like I said, find the existence of a target value in a list or collection of values. Say, for example, we have a list of numbers. We want to find out if a certain number is a part of this list or not. If it is a part of this number, we tell where is it in the list. So, which means that we return the index of this item. If not, maybe we return some special character, or perhaps, let's say, an exception. In this case, in case, let's say there are multiple occurrences of the value, well, we may return the first, the last, or say perhaps any occurrence. Like I said, this is a fundamental problem with many, many, many applications in, let's say, computing. Lots and lots of problems, in fact, fall in this bracket, even though sometimes they may not obviously look like this, right? Sometimes they may not be so well structured to start with, where we have a list of values and we find existence of a given value, but those problems eventually can be cast in this form matter, right? So that's why search becomes very interesting and also very, let's say, fun to think about, right? Let's take an example. Let's say we have a list, this list given here. So I ask a question, is 2 a part of this list? If yes, which position do I find 2? Well, we know that from visual inspection that 2 is on item 1, basically item 0, item 1. Remember, Python indexing starts at 0. So 2 is at index 1 on this list. On the other hand, 28 is not a part of this list, right? So in this case, the list is very small. We can visually do it. But just imagine doing this on a list which has got millions of items or maybe more. We can't do this visually. We need a proper algorithm to solve it. And that's exactly what we mean by search algorithms. And that's the kind of focus on, let's say, this set of videos. Basically, the key learning goals we have from this is to learn about linear search, which is kind of, you can say, the first starting point, naive algorithm. It turns out that linear search is really, simple in some sense to understand, but also really all that we can do with the data being unstructured. So we look at the best case, worst case, and the average complexity of linear search. Next, we'll start seeing that, okay, look, let's say if the data had some structure, in specifically speaking, if the data was, let's say, sorted, right? Maybe in ascending order, descending order, we could do something more, which is more efficient than linear search. For example, we can do jump search, or the king of all, the binary search, right? So we will understand what jump search is, what binary search is. In fact, we'll see how we have already seen this as part of a Python curriculum, but we'll go a little bit deeper into their implementation and stuff. We'll understand the implication of the logarithmic complexity. Now, this is a very important concept. Binary search basically learns in complexity of log of n, and this is significant, right? So we'll do a comparison of linear search, which is linear, in n, so increases linearly. Jump search, which as we'll see later is square root of n, and binary search, which is log of n. And we'll see, seeing all this, why for a sorted list, in fact, binary search wins. Binary search is really the king. So if at all there is one message I wanted to take from this, it is that, look, if you have a sorted list, and you want to run some kind of search on that, well, think binary search, because that is a very, very, very efficient algorithm. As always, we are going to approach this in a systematic, step-by-step manner. I hope you'll enjoy this journey. As we have spoken before, YBite Algorithms and Olympiad Track is meant to go deep into algorithms in a lively, fun manner. And that's what we're trying to do here. Look at our website, www.ybite.in, to find more such content and enjoy programming. Take care. Thank you so much. Bye-bye.